Hi everyone, welcome to TechMaestro. My name is Karan and this video marks the beginning of the data structure stacks. In this video we'll learn what stack data structure is, what are the different operations that stack supports, and at the last, the very important part, which is like how can you identify if a problem can be solved using stacks. So without any further ado, let's start with stack. So first of all, what stack is? So a stack is a data structure which supports last in first out kind of operation. What it means is, let's say, let's try to basically mimic this using a real life scenario. So you would have heard things like stack of plates. What it means is like there's a plate on top of that. If you add one more plate on top of that, you add it on top of this. Like now, if you have to remove a plate, the the plate that was added the latest will be removed first, and then all other plates, right? So basically, similarly, when you add a data point to one uh, data point in a stack or a data in a stack, basically you add it on the top of the existing, and only when you remove the topmost, you peel off the topmost data point, then you can reveal or access the data point at the bottom of the list. So what we said is, let's say if this is a stack, initially it's an empty stack. So when you add something, you first add it here. Then second thing, let's say I add my second data structure, second data, it will get added here. Third will get here, and fourth here. Now, when you say, okay, let's remove the data out of the stack, the first data that can be taken out or accessed from the stack is the green, then blue, then red, and at last you can access black. So this order is very well defined in stack. This is what stack data structure is. So basically what we have said is it supports last in first out operations. So the element which was added the latest is taken out from the stack at the very beginning, or the very first thing that is taken out of the stack is the element that got added at the last. So what now let's see what are the operations that stack data structure supports. So the operations that we can do on a stack data structure is one, push. So the operation push basically means adding something on the top of the stack. When you push something, that data get added on the top of the stack. In this case, when we added black, so it got pushed in the stack. Then red got pushed in the stack. Then blue got pushed in the stack. Then green got pushed in the stack. So this is basically a push data structure, push operation in the stack. Then the second operation that stack supports is pop. Pop basically means taking the data out, taking data out of stack. This is what pop basically means. So you basically, when you pop out, the topmost thing is taken out of the stack. So in this case, green will be taken out of the stack. Then blue will be taken out of the stack. Then the third operation commonly present in stack is peek. So what peek means is giving me the value of the top of the stack. It does not take out anything. It only returns the topmost value of the stack. So we will see example of each and all these operations in the further below, like in the video further. Then fourth operation that we have is empty. So this is a very simple Boolean kind of operation which tells whether the stack is empty or not. Return true, return true if empty, else false. As simple as that. Return true if empty, else false. This is a very simple operation. Now let's see how can we implement stack using linked list. So a stack can be implemented using both an array or a linked list. Let's see how can we do that using a linked list. So next part is actually implementing stack. So stack using a linked list. So If you haven't checked the linked list series yet, if you don't know what linked list is, how do you insert a value in a linked list, or how you search a value in a linked list, or delete a value in the linked list, please go and check the previous series of linked list, where you can figure out or learn the basics of linked list data structure, so that this can be used. That is basically a prerequisite for this lesson. Now, so let's say initially there is, let's say this is my, I'm just taking a random example, and we will see all the operations. So let's say this is my stack. This represents my head, and this represents my tail. So whenever I add something in a stack, what I do is I append at the beginning of the stack, or basically the linked list. So if this is my linked list, if I append something new, I append it here in the beginning. So let's say I have to add a value X here, add a value X in the stack. So what I do is I first mark it, mark the next of this new node X as the head, to the head of the linked list, and then move the head to this, because I am appending at the beginning of the linked list. So basically the new list will become something like this: 1, 2, 3, and my head points here. So the operations that we did is, let's say this is represented by a PTR. So PTR dot next is equals to head, and head equals PTR. As simple as that. So these are the two operations. Notice here that the operations, like let's say these, I name it 1 and 2, the order of the operations is very important. Let's say what happens if I change the order. What if I reverse the order of these? Let's say what will happen. So if I move my PTR, if I move my head first to the PTR, what will happen is, so let's create a new linked list, so that, and X. So X currently points to null, because this is a totally new list, and this is my head. If I move my head first, it will go here. It will go here first, right? And then as a next step, what will happen is, if one first it will go here, and it will look, the list will look like something like this. And I have no way to point or to identify this, the previous linked list or the previous tag that I have. So if I change the order of these two operations, I will end up losing the entire linked list. So the data inconsistency will be there. So that is why the order matters in this case here. So moving on to the next operation, which is pop. So the second operation that we have is pop. So what is pop? Like we discussed earlier, it is taking the data out. So in this example, let's say I take the same list. What is the data at the top of the list? X. X is my top of the list. So if somebody says, okay, pop the topmost element from the stack, I have to return X, and I have to move my head to the next node. So what do we do? First, we take a PTR which points to head, because I need to maintain a copy of this. Then I move my head, and then the next step is ptr.next is null. So if I have to take this node out, I have to break this chain, right? This is the only point that you will end up removing the node from the list. Otherwise, if you don't break this change, this node still exists in the, this node still exists in linked list. So you have to break the chain. So this is the step that do that. Again, these are important. The steps are important, because like we discussed earlier, if we don't do that, we'll end up basically creating dangling pointers, or we'll end up losing the data itself. So as a homework, do one thing. Let's do one thing. Go and check what happens if I change the order of these. Can I change, or can I not change? If I can, what is that change? Or why cannot, the why part as well, like why would something, what will happen if I change the order? Then the third part is push, sorry, this is what we have already done, push, pop, and peak. So peak, now let's see what peak is. Here we discussed that peek is give me the topmost data, just return the value of the topmost data and do not take anything out of the stack. So all it does is just return head dot val. Simple. So in both peek and pop, there's a catch. You have to identify if stack is empty or not. So if stack is empty, there is nothing to give out of the stack, right? So in both pop and peek, only return when stack is not empty. If stack is empty, it may be an error or it may be a null return value. It depends on the use case that you are using the stack for. And the fourth operation that we have is empty, is empty. Here all we do is return head equal null. So just by doing that, you can know that if the stack is empty, my head will point to null. If it is not, head will point to some or the other node. So this is as simple as that. As a homework, what I will suggest you do is like this is a pseudocode kind of thing. What I'll suggest you is like go and actually implement that in the language of your choice and try out all these operations so that you are very clear on how stack actually work. As a next step in the video, as promised earlier, we'll see how can we identify if I can implement stack in a question or not. So there is a very good catch or a very good point that you can keep in mind while basically this is the these are the steps of identification that you can do to identify whether a stack can be implemented or not in or applied in a question or not. Identify if a DSA problem can be solved using stack. And in fact, in the following videos of the series, you will see that the 2 points that I will mention in that I will mention here will basically see that okay, these two are the identification point, and yes, I am able to solve that question using stack in a much better optimized way. So two things are: one, your brute force solution is of n square. This is one, and two, your inner loop. Since this is n square, there will be two loop, outer loop and inner loop. Your inner loop is function of function of outer loop. Okay, now what does this statement mean? So since this is again, this is n square, so there will be two loops. So let's say for I equals 0 to n and for j equals something. Now, what does function of outer loop means? It basically means my j can be, my j is basically dependent on I somehow. What is that dependency? It can go from 0 to I. This is one sort of dependency. Basically, my j can only iterate till I, right? Oh, and in this case, j is incrementing. Other possibilities from I to 0. And in this case, my j is decrementing. So let's say if this is my j can go from here to here, or my j can go from I to 0 as well. What are the two other possibilities? If you look at the diagram again, it is also possible that j can move from I to n, right? And what is the next and the last possibility? J can go from n to I, right? A j can go from n to I, j minus minus. So whenever there is a brute force solution, O(n) square, and this condition is there, the chances that this question can be solved using stack is very high. And I will prove all this hypothesis in next 4 or 5 videos. All the videos that will, all the problems that we will solve using stacks, all the theory and the basics that we will build will be uh, uh, will be a testament to these 2 points basically. So what I'll suggest is like tune in till the last of the stack series so that you can basically get better in the stack. If you like the video, please click on the like button. Comment below what you want me to make the video on next. And don't forget to click on the subscribe and the bell icon so that you can get the notification as soon as we upload new videos and you can learn along the way. Thank you so much. See you in the next video. Bye bye.